I'd like to continue with our pinky length problem, looking at standard deviation, and I'd like to throw something new at you. Last week, when talking about our measures of central tendency and the mean and the median specifically and how outliers affected it, we learned that the mean is much more sensitive to outliers than the median. And by the way, several of you I asked, well, isn't there a case, can you think of a case when throwing a couple outliers at the distribution does not affect the mean? And the answer, as some of you figured out, was, well, if we have a mean here and the outliers are equidistant from, from the mean, well, then they cancel each other out and they don't change the mean. But what those outliers would still do is cause a greater spread or a higher standard deviation in the distribution. Let's see how that works. Let's go back to our distribution here, and I've started to draw some figures in. I've added a couple outliers out here at -6, and I want to recalculate standard deviation. So what I've done is added my two -6s to our standard deviation. And I'm going to have to pull this up for now so we can see things. And let's see, what do we have? When we add those values, the sum of the values was 21, but now if we subtract 12, the sum of the values, sum of the x's is 9. And so to calculate our mean value, we have 9 divided by, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9 values. So we have 9 divided by 9, and our new mean is at 1.0. Likewise, let's see, back to the distribution, we have to square those values to get the squared deviation. Well, wait, deviation from the mean, x minus x bar. I did it wrong. I have to back up. Hold on one sec. Okay, I calculated our sample mean correctly. If we add up our 9 values, they add to 9, and there's 9 of them, so our sample mean is 1. And now we have to calculate our deviation from the mean and our deviation squared. So we have the green column now we're looking at. We have our value of x minus the sample mean of 1. 1 minus 1 is 0. 2 minus 1 is 1. 2 minus 1 is 1, 3 minus 1 is 2, so on and so forth. We get down to the end. -6 minus 1 is -7. Okay, so we have those 9 values in green, and now we need to square them to get our squared deviation. 0 squared is 0, 1 squared is 1, blah, blah, blah. 2 squared is 2, 3 squared is 9, 4 squared is 16. -7 squared is 49 once. We have 2 of those, so I have 2 of them over here on the right. And then we need to calculate the sum of our squared deviations. So if we add up those 9 values, I got 138. And we can now calculate our new sample deviation. And I've done that at the bottom. Sample standard deviation is equal to the sum of the deviations squared, 138, divided by n minus 1. That's 9 minus 1, that's 138 over 8. Square root means the square root is 17 1/4. And we end up with a sample standard deviation of 4.2. Well, look, in the prior case, we had a sample standard deviation of 1.4. 68% of our values were the mean of 3 plus 1.4 and between plus 1.4 and minus 1.4. Well, now our sample standard deviation has jumped up to 4.2 just because we had a couple outliers. The data is more widespread, and that sample standard deviation shows us that. Let's go back to our number line. Here's our original number line. Originally we had a sample mean of 3, and when we placed in those plus or minus 1 standard deviation, we found, what was it, gotta get the other sheet, that 71% of our values, here it is, 71% of our values fell between plus and minus 1 standard deviation from the mean. which was real close to the 68%. That's theoretical. Well, now in our second case, we have a sample mean of 1 and a sample standard deviation of, what was it, 4.2. Thank you, I heard that. And let's plot those values. So let's see, we got it, our new standard deviation, I'm sorry, sample mean is here. X bar equals 1. Oh, I wish I had some more space. That's okay. We'll get by. So it's changed from 3 down to 1. And now if we add 4.2 to 1, we're up at 5.2. Let's draw that line in. 5.2. There's 2, 4, 5. 5.2 is somewhere out here. 5.2. And if I subtract 4.2 from 1, I'm going to go what? To, oh boy, let's see, 1 minus 4.2 is going to be negative 2.8, negative 3.8. Oh, I got to double check this. Hold on. How embarrassing that I can't do simple math in my head. All right, so I've drawn in a bell curve for our problem once again, and sure enough, 1 minus 4.2 is negative 3.2. 1 plus 4.2 is 5.2, so we're in the process of drawing those in on our number line. Let's see, negative 3.2, where does that fall? There's negative 3.2, something like that. Negative 3.2. So now, our mean again is here in the middle, and 4.2 on either side of it is supposed to capture, again, 68% of our values. Well, how many did we capture this time? Let's see, we captured all of this group, 1, 2, 3, 4, 5, 6, 7, but neither of the two outliners. So this time, we captured 7/9 of the values, and 7/9 is about 78%. So it's a little worse in terms of accuracy, but again, it is because we have a small sample with just a relatively few number of values. You can't expect it to be exact. However, this technique gives you a rough idea how close you are. Oftentimes, planning is done in terms of standard deviations away from the mean. Our author alluded to it when he said they're planning the size of airplane seats. Well, they know that 60% of the population is going to have a butt width of, I don't know how many inches, plus or minus 1 standard deviation. And maybe they use that, plus or minus 1 standard deviation, as their design size. And make it large enough for that the person who is plus 1 standard deviation greater than the mean. Okay, I hope this problem was helpful. You're going to have to calculate standard deviation. It's really not so tough. Interpreting all these numbers, that's the tough part.